All right. Welcome back, ladies and gentlemen, to this third and final installment of the Matlab Comedy Hour. Yeah, that's kind of corny. I realize I was trying to make this a little more interesting than just a programming video. All right, well, as I said, we're going to add, let's go to the PowerPoint. We're going to add this exact result from integral calculus and compare it to our computational solution. So that's the next goal. So if we go back to our script here, and I'm just going to intersperse this into what we already have. Here's the script we've been working with, and remember we ran this and we get the correct qualitative behavior anyway. Now by comparing our computational solution to the exact solution we get from doing the integral, we'll be able to inspect and systematically check the accuracy of our computational solution. All right, so what do? Let's go to these pre-allocated arrays, right? And in the list, I'm going to add another one. I'm going to call this velocity underscore exact. Oops. All right. And this is going to be another array of the same size we've been creating. We want n, where n is some number of iterations we've indicated here. We want it to be the same size as the other arrays because we want to make a comparison, right? Let's see. Now, what we're going to do with this exact velocity, we're going to populate the memory locations in velocity exact array with the values of the function. What function? This function right here, this hyperbolic tangent result for velocity, because we want to make a comparison of the velocity ultimately. We're going to evaluate this function at each successive time, which means we're going to use the time array for evaluating this back in the script here. All right. Now, let's go ahead and also give this an initial condition, which just means I'm going to evaluate it at time 1, which is 0. All right. Now, let's do this the long way. We could look up the hyperbolic tangent function. Let's go back and look at it here. If you put in 0, basically the hyperbolic tangent of 0 is 0. So we could put in 0 here for the initial exact solution at time 0. But let's go ahead and program this in for two reasons. One, well, actually this was derived under the assumption that the initial velocity is 0 at time 0. So it's really not necessary. But let's go ahead and program it anyway. All right, and then we'll just copy and paste when we put it in the loop. I'll go ahead and do it, and you can see what I'm thinking here. So velocity underscore exact, all right, of 1. All right, this is the first memory location, equals, and now we're just going to do what that equation says to do. So let's start with this coefficient in front. It's the square root of 2mg over d rho a. So let's remember that, 2mg over d rho a. The square root in Matlab is sqrt. All right, so it's 2 star m star g divided by, now I got to do quantity here, d star rho star a. All right. That's going to be times the hyperbolic tangent, and Matlab has a built-in, I don't know, what's this thing doing here? Okay. Matlab has a built-in hyperbolic tangent function, so we can just call it TANH, right? The hyperbolic tangent of, right, now let's look back at the equation real quick. There's another square root of stuff here, and then times the time, and it's going to be t, or the time at that current step, that current time step. So let's do the square root of the stuff first here. So that's going to be d rho ag over 2m. Let's remember that. Right, so it's going to be square root of d star rho star a star g. I believe that's correct. Get rid of that thing. Divided by quantity 2 star m. All right, that's all in the square. That's the quantity in the denominator. I need one more parenthesis to close off the square root. And now we're going to multiply that by the current time, which in this case we're not in the loop yet. The current time is the initial time, time of 1. Time of 1, right? And we need one more closed parentheses here to close off the tangent. Right? And I believe that is correct. Right? We terminate it with a semicolon. Right? And that looks good. One thing you'll notice as you're using Matlab here, you see this little square over the right. I'm going to try to emphasize it here. It's red right now, and if I move my little arrow over the top, it says warnings found. Click to go to the next message. You can see a little line down here. See this line? So let's hover over that and see what it says here. Line 30, invalid syntax. Possibly something's missing. All right, so I may not have this correct. So what is not right? It doesn't like something here. I'm going to stare at it for a moment. That closes that. That closes that. We'll try to run it. Looks okay to me. Actually, I'm not quite sure, but well, we'll know soon enough, right? Now, this is the exact function at the first time. Now, if we inside the loop, we're going to have to do the same calculation. So I'm just going to copy and paste the thing like this. But now this has to be index I, because we're looping for from 2 all the way up to n, and then this over here has to be I also. Right? And of course that's going to yell at me over here and say something could possibly be missing. Let's look one more time here. That closes the square root. So it's the square root of that stuff times the time, and that closes the tangent. Ah, there is something. See this? I have the square root. I haven't closed the square root over here. Wow. All right. So see the denominator d rho a is enclosed, but I haven't closed this parentheses off here. So I'm going to do that. Right? And then let's do it this way. So you should always pay attention to your warnings over here. Notice by correcting that, I have a green square now. See that? No warnings found. Right? So that's kind of nice. MATLAB's watching out for us. All right. So now, assuming we have this programmed correctly, all right, we are calculating the Euler approximation for position and velocity, and all we're doing with this velocity exact, remember, is evaluating the function at different times. Right? That's exact, and now we want to compare the two. The easiest way to do the comparisons, go back to this plot, all right, plot time. We're going to change this back to velocity. We want velocity versus time. By the way, if you look at this slide again, we could program in the position y of t and make a comparison with position also. I'm going to leave that for you to do, right? All right, so how do we make the comparison? If you put in the same plot command here, time, velocity, now we want to plot also velocity exact versus time, so we just add this. Let me type it, and then you can take a peek and think about what this will do. This will put velocity versus time, that's the first pair, inside the parentheses for the plot command. And it will also include velocity exact versus time. So the way you put more than one curve on the same graph is just to add them in this manner here. Right? That's the syntax. By the way, I think you already realize the plot command connects the dots. Remember, in the Euler method, we're only producing solutions at discrete times. And so the plot command just connects the dots, right? So if we put the times close enough together, you can't tell that it's discrete. This just makes it easier because it connects the dots with lines. It makes it look like a continuous curve, and it makes it easier for comparison. Right, there's a bunch of other possible ways to plot the data, but for now we'll just keep using this. All right, so let's do this, and let's do a comparison here. All right, so if I run it, okay, now this looks pretty good. So I think we've got it programmed properly. Let me blow this up a little bit here. All right, and it's a little hard to see. If I add a legend, I think I can do this maybe here. Insert legend. Let's see what it does. There we go. All right, so you can see this points out that we've got two things plotted. All right, now I've done this enough to know which is which. The red one here, if I go back to here, the blue one is the first pair, the red is the second pair. So the red is the exact, the blue is the Euler velocity versus time here in the plot command. So let's look at the plot again. All right, remember this is velocity in meters per second vertical, time on the horizontal. We're limiting the plot to 15 seconds, right? Now, this looks pretty good, except you can kind of tell in the middle area here, there's not very good agreement. But look, on the ends for high times and for low times, all I can see is red. That means the red's overlapping the blue, and that means the solutions are almost identical. But if you look closely, I'll zoom in on this in a minute. If you look closely right in this middle area, in the neighborhood of 3 or 4 seconds, they're not matching perfectly. Now there's a way to zoom in here. Choose this little magnifying glass thing and create a box, and whatever the box surrounds will become the new graph window. Right, see that? And you can clearly see the red is the exact solution and the blue here is the approximation, and they're not matching. So the question is, how accurate is this blue one? And just by looking at the scale, you would say pretty close, but pretty close isn't a very good quantitative way to describe how accurate your solution is, right? But let's do, before we think any more about what it means to have an accurate solution in this context here, let's systematically change delta t and see what happens. So I'm going to kill this one here. And back up here in the script, have a look. Remember we set delta t equal to 0.1 originally. So what I'm going to do is change this. Let's make this a little bigger, actually. Matter of fact, let's make it a lot bigger. Let's make it 2 seconds. All right, it was 0.1 second. Let's make it 2 seconds and just see what happens. Now this will not affect the exact velocity calculation, because you can see both here and in the loop down here, right, both this line, what is that, line 30 as well as line 37, there's no dt showing up. We're just evaluating the function. However, this will affect the approximation, right? Now dt 2 seconds is what I just put in, as opposed to 0.1 second, tenth of a second. This is a lot bigger, and so we would expect it to not be as accurate. Also, keep in mind what we're going to see. We will be producing an Euler solution every 2 seconds now, and so if I take the calculation out to 15 seconds, there's only about 7 2-second intervals, 7 or 8 2-second intervals in that 15-second period. So the solution will only have 7 points. Right? Well, here, let's have a look. Let's run it. All right, and look what we have here. Right? Okay. Now remember, the red is the exact, and now you can see the discrete nature of what we're calculating here. We're only producing both an exact solution as well as an approximation at these different times. This is the 2-second solution for each. Here's the 4-second solution, 6, 8, 10, and so on. And you can see we're just simply connecting the dots with a straight line. All right. So it's really these discrete solutions, these points we're comparing. But look at what we've produced. Here's the red, and that is just what the solution looks like at these different points. Remember, we're only producing a solution at the times we tell it to, which is every time step. All right, every 2 seconds. But look at the blue. Look at what the blue does here. It's not anywhere near the red one, but look at all this weird stuff happening. It kind of goes up, it maximizes, then it comes back down, and it seems to oscillate about some point. All right, now that's this we call in computational terms, this is an artificial behavior, right? Wouldn't it be incredible if you dropped a ball and its velocity would somehow oscillate about a terminal velocity? And of course we don't see that. That's not observed. That's rather nonsensical. And so you can see that this is an artifact, or an artifact of the value of delta t not leading to an accurate solution. All right, so remember what this one looks like. Let's kill this graph now. You can rewind the video and look at it again if you need to. And let's change delta t, let's change it down to 1, from 2 to 1 second. All right, so we're going to systematically lower delta t. Now let's run it. All right, now look at this. Remember, we're generating solutions every 1 second now. So between 0 and 15 seconds, there's now 15 points that have solutions. But you can see it matches pretty well up here for higher times and for the low times, but there's this little gap in the middle which suggests our solution is not yet accurate. Right? And it's actually a pretty significant gap. If you look closely, the difference, say at the, I don't know, what is that, the 3-second solution is about 7, it's about 2.5 or maybe 2. If this is what, 18 and this is 20, that's about a 10% difference in the solutions. Right, which is not very good accuracy. Right, let's kill this. Remember what that one looks like? Let's lower delta t to 0.5 second, to 0.5 instead of 1. And you can see, as expected, it's better, although there's still a gap here. Now the gap has narrowed. Instead of maybe a 10% gap, it's maybe 5% now or so. I mean, we could calculate this more accurately. Again, at the long times and the early times, we have pretty good matching solutions, but there's this gap in the middle, right? All right, kill this one off, and let's go back from here. Let's go back to that 0.1 second. That's what we started with. And this actually looks pretty good, doesn't it? Until, again, we zoom in. Now, you can barely see this, and you might say, well, isn't this good enough? Right? And so I might just pause for a moment and address this concept of good enough. Is that blue solution on this scale anyway, is this close enough to that red line everywhere that we can call it accurate? The simple answer to that is it depends. It all depends on our tolerance for error. All right? If we're dropping a ball, for instance, from the Sears Tower, and we were going to use this model to try to match our experiment, and you can see for these middle times here, I don't know, what is that, a 1% difference in the solutions? You probably wouldn't even be able to measure the accuracy of the position. In other words, you wouldn't be able to measure the position of a falling ball any better than about a plus or minus 1%. So in that sense, if all we're interested in is doing an experiment and matching the experiment with this model, that's probably close enough. If, however, you're designing an important piece of equipment that someone's life depends on, for instance, say in the medical field, then maybe a 1% difference is just not acceptable. And so these are things you have to think about when you do your computational solutions. All right, can I live with this, and is this difference that I'm observing here, is this inaccuracy problematic based on my error tolerance, right? And every situation is different. So the best way to deal with it is to quantitatively measure the difference and report it, and just get used to pointing it out and try to estimate for whatever application you're thinking about some type of error tolerance, some type of quantitative way of assessing this. Well, let's keep going. Let's make this even smaller. All right, now keep in mind, if I make this smaller, remember I've taken this out 1,000 iterations, and if I multiply 1,000 times each time step, that tells me the total time that I've calculated. So for instance, if I make this 100th of a second, if I make that 0.01, now that's 1/10 of what I was just using. It was 1/10 of a second, now it's 100th of a second. Okay, let's get rid of the graph so it'll pop up for us again. All right, and let's run it. Now, this is why I was pointing that out. We've only gone out 10 seconds of actual simulation or model time. Remember, 1,000 times 0.01 gives us 10 seconds. If I wanted these to extend further, I'd have to run it more times. We can do that very easily. Let's just change n to 2,000. And you can see that it doesn't take that long to run at all. Right? 2,000 time steps are almost instantaneous. The graph pops up, and you can see it's gone out here again because now we've taken it out. 2,000 times 0.01 is 20 seconds of time. We're limiting it to 15 here. All right, now look at this. Let's blow it up a little bit. If you look closely, you might sense a little, your eye might pick up a little dark color in here. Not really. I mean, it's pretty darn close. But remember now, we can always zoom in. So let's zoom in here. I'm grabbing this positive magnifying glass, right? And I zoomed in, and you can see a little blue. If you look really closely, you can see, but still, right? Still pretty darn close. So let's zoom in here. There we go. Now you can start to see a separation. The blue, the approximation, as before, although it's closer to the red, it's lying above it. Let's zoom in a little more. Now it looks like they're separated quite a bit, but look at the difference now. Look at the vertical scale here. From this point to this point, each of these marks here are 0.05 separated. And so if you take this distance, this is a fraction of a percentage difference in the solutions here. Right? We're starting to get very, very accurate here, even though I can always zoom in and see that they're not matching perfectly. Right? So what I've showed you, right, by systematically lowering delta t, is that this blue solution is farther away from the red exact one the greater delta t is. If we were to put all of those different values of the solutions for the different values of delta t on the same graph, you would see a whole family of curves of blue showing up. And as you lower delta t, the blue would approach in this direction here. You can see that little plus sign. It would approach the red as I make delta t smaller. In the limit that I could make delta t 0, then the blue would exactly match the red, but then again we wouldn't have an approximation anymore, would we? That would be calculus, and it would be the exact red solution. All right, so you see how this works. This also sheds light on how to check the accuracy of a solution if you don't actually have the exact solution to compare to. Right? Systematically lower delta t, whether that red line is there or not for comparison, you would observe that blue line slowly march toward some position, and as you lowered delta t and lowered and kept lowering it, making it orders of magnitude smaller, it would no longer move very far with continually lowering. So you see a convergence. That's what we really are looking for. That's really the main thing to take away from this. The convergence of the the approximate solution towards the exact solution. All right. Okay. Well, I'm going to leave it to you in the exercises of that first. By the way, you should play with this. All right. I'm going to. This is on our Sakai website under resources. It's the Matlab script. I believe it's called Falling Sphere. Also, I have put on there, I believe, the same Falling Sphere program we've just built together in Matlab here. I've also included implementations in Python, in Fortran, and in C, C++ also, if you want to take a look at those. Again, once you have seen the components of a programming language and how to build a simple model, it's not hard to do it in other languages. The main difference is the syntax and the way the commands work. Right? So I have those on there. You can take a look. And you should play with this. Just be curious. Try different things. Also, try to answer the question. We've only looked at really velocity here. You could try to plot position again and try to answer the question, how long would it actually take the basketball to fall from the Sears Tower? All right? Okay, that's all for now, and I will see you soon.